Okay, here's lesson 9 in our continuing unit on energy. Again, the next 3 lessons, 9, 10, and 11, are devoted to one special type of energy consideration, and this is, of course, nuclear physics. It's a branch of science that studies the components and the interactions of atomic nuclei, and really it's a very, very interesting part of science, mainly because of its applications. Of course, we've all seen the devastation that's caused by atomic weapons and weapons of mass destruction. Because in southern Ontario, a lot of our energy, household energy, is produced in nuclear power plants. It's a very important part of Ontario power generation. And some of you have probably had an X-ray at some point. Really, diagnostic medicine and therapeutic medicine relies heavily on radiation that we would see in the form of X-rays, etc., etc. And so this is some of the applications of what we're going to be talking about in the next 3 lessons. So let's start by talking about the structure of atomic nuclei. Okay, so we know that all matter is made up of atoms, and atoms consist of course, a nucleus that has positive charge, and of course that nucleus is surrounded by negatively charged particles called electrons. We know this. Okay. The study of electricity is really all about electrons. The study of what we're talking about now really looks at the inside, that nucleus of atoms in much more detail. So we're going to concern ourselves with protons, neutrons, and atomic numbers. Okay, so here we go. Again, this is kind of the quantum mechanical notion of the atom. You don't have to draw this. This is just something that I put in here. But really, all of this, not important. This right in here, bing, bing, bing. This is all we care about when we're talking about this kind of physics. Okay. Particles with positive charge are called protons. We know what the charge on a proton is. It's 1.622 times 10 to the negative 19 coulombs. This is our SI unit of charge, coulombs. Okay. It's not, the charge on a proton is not +1. It's positive 1.622 times 10 to the minus 19 coulombs. We also happen to know the mass of a proton. They're tiny, 1.67 times 10 to the negative 27 kilograms. Neutrons, very similarly, are particles that have a mass of 1.67 times 10 to the negative 27, excuse me, but very dissimilar to protons, they have no charge. Okay, so they are neutral. The atomic number we give the letter Z to, and basically this is the total number of protons or electrons that are in an atom. Okay, so if you see the periodic table and you notice how it's arranged, it's of course arranged by atomic number, and that atomic number is the number of protons or electrons that are in an atom. The mass number we give the letter A to, and that is the number of protons plus the number of neutrons in an atom. So basically it breaks down like this. Any element, X, has the mass number and the atomic number. Usually the mass number is given up top. The atomic number is given down below. This is certainly the way our textbook does it. The element symbol will be here, and of course the mass number and the atomic number are here. Okay? So let's move on just briefly to talk about this example here. Some atom, it has a mass number of 238 and an atomic number of 92. What's the element? How many protons, neutrons, and electrons exist in this atom? Well, to identify what the element is, we're going to need the periodic table. So we can get that in a moment. But Z, this number down here, is the number of protons. So we know that it has 92 protons in it. Z is also equal to the number of electrons, but A, which is this number up top, is the number of protons plus the number of neutrons, and that's 238. Okay, so if we said that 238 is this 92 plus the number of neutrons, we can simply subtract off the 92, and we get 146. So there's 146 neutrons in this element. All atoms in general are neutrons. excuse me, are neutral. If they weren't, they would be considered ions, and this is not an ion. So the number of protons must balance the number of electrons, and we get the number of electrons is 92. Okay, so not that much of a stretch so far. What element is this? Well, when we check the periodic table, this is, of course, the element known as uranium, which is very, very radioactive. And we'll see why in a couple minutes. All right. Isotopes. Something that perhaps you've encountered in your science background. Something that we can talk about now, just briefly. Isotopes are the same element, right? So they've got the same chemical properties. But each isotope of a different element has a different number of neutrons inside of its nucleus. So the additional neutrons don't change the electrical charge of any atom, right? So they don't change the chemical properties, but they do change the nuclear properties, okay? Hydrogen has 2 isotopes, for example. Here's hydrogen right here. Hydrogen has 2 isotopes. This isotope has 1 neutron. This isotope has 2 neutrons. This we call deuterium. This we call tritium. And these are both basically found heavily in the sun. We'd see a lot of deuterium and tritium in the sun because they're involved in nuclear fusion. And we'll talk about fusion and fission in the final lesson of this unit. All right. So what's radiation? We're talking about all this for a specific reason, and it's so that we can quantify radiation. Okay. Inside any atom, we got positively charged protons, but positively charged protons, we know, should repel each other. And so the only reason that a nucleus doesn't fly apart is because these neutrons kind of act as like a glue, okay? And it's accomplished in several different ways. Basically, they dilute the repulsion of the protons, and at extremely close ranges, there's a force of attraction between a neutron and a proton. Okay, and we're not going to get into that, but this is one of the 4 fundamental forces of nature, and for now, we're just going to call it this nuclear force. Okay, so a nuclear force kind of keeps the atom bound together, right? And due to the fact that atoms have a different number of neutrons and some atomic nuclei are more stable than others, right? Atoms with too few or too many may become unstable. And we know that when anything's unstable, it always wants to get to kind of like a place where it is stable. So very often we'll say that these atoms are living in a high energy state. Their nucleus exists in a high energy state. So they might spontaneously break apart at any time. And when they do break apart, energy is released, and that's radiation. Okay? So radiation is really anything that radiates away from a nucleus in the process of that becoming more stable. And that's what we call decay. We've noticed that there's several different ways that this can happen, and we're going to take a look at those things now. So one of the first and most common is called alpha decay. Okay? And alpha decay is the most common way for a nucleus to decay. Basically, what happens is that it emits an alpha particle. And an alpha particle is 2 protons and 2 neutrons. Right? So if you know your periodic table, oh, that's nothing really other than a helium nucleus. Okay? This type of decay is mostly found with heavy elements, so uranium, plutonium, all these big heavy elements. They have many more neutrons than protons. And so if they lose 2 of each, then the protons of proportions left is more than that of the neutrons that are left. And the whole, overall, everything becomes more stable. Okay. Marie Curie, one of the founders of this type of science, discovered this type of radiation with radium. And here is the decay equation that's associated with the alpha decay of radium. So radium, which has a mass number of 226 and an atomic number of 88, decays by alpha decay into radon, which has a mass number of 222 and an atomic number of 86, plus an alpha particle. Okay. There are 4 other mechanisms of decay that you need to be aware of. and I leave them to you to read in your textbook. Read and summarize with a few pertinent bullet points from the description. Beta decay is very important. Positron emission and electron capture, or gamma ray emission, are interesting and for your enjoyment. Beta decay is very, very important, though. These two rely heavily on your understanding of some weird and wacky science, and so you can kind of take a look at them and just say, "Holy cow! I didn't even know what a positron was." But these I leave to your reading. Okay, so here's example number 2. Let's look at these two decay equations and let's fill in the missing information. All right, so radon is decaying into polonium. We'd like to know what this particle is that is released. Okay, so we know that the mass numbers have to balance. This is the conservation of mass. So 222 is equal to 218 plus A, and 86 is equal to 84 plus Z. If A is equal to 4 and Z is equal to 2, this must be an alpha particle. Okay, so that's your giveaway. But when you do this, whenever you get 4 and 2, you've got an alpha particle here. Here we've got Neptunian, and it's decaying into something plus this little electron. And so whenever we see this, 239 equals A plus 0, and 93 is equal to Z plus -1. So what does this become? 239 and 94, which is plutonium. So Neptunian decays via beta decay and basically becomes plutonium. Okay, so this is kind of the introduction to this unit, and we'll see you next lesson when we talk a little bit more about decay and the mathematics behind decay.